everyone, I'm Nurul Hazrina binti Nordin from UMPSA STEM Lab, the Faculty of Electrical Electronics Engineering, University Malaysia Pahang Al Sultan Abdullah, the instructor for this course.
Welcome to Microcredential 3 Raspberry Pi Programming, the final module in our structured learning series. In this course, we will integrate Python programming with hardware, utilizing Raspberry Pi systems and microcontrollers like the Raspberry Pi Pico to develop innovative real-world applications. This course builds upon the foundation laid in Microcredential number 1, Learning Python through Slider Game Development, where students mastered programming fundamentals. Microcredential number 2, Raspberry Pi Installation and Configuration, where students learn to set up and configure for Raspberry Pi for hardware interaction. And Microcredential number 3, Raspberry Pi Programming, which is this course. We will write Python programs to interface with hardware components. And Microcredential 3, Raspberry Pi Programming, this course, where we will write Python programs to interface with hardware components. So this course basically is designed to bridge the gap between software and hardware, covering essential topics such as Chapter 1, Introduction to Raspberry Pi. Here, you will understand the capabilities of Raspberry Pi for hardware-based programming. Chapter number 2, Control Flow. Here, you will learn about loops, conditionals, and functionals to control hardware interaction. Chapter number 3, Working with External Libraries. Here, you will explore third-party Python libraries to enhance Raspberry Pi functionality. Chapter number 4, Interfacing with Sensors. You will learn to connect and control sensors and actuators using GPIO pins and Python. And finally, chapter number 5, where you will learn about cloud integration, networking, and communication. Here, you will do activities that will send and receive data via the cloud, enabling IoT applications. A major project in this course will involve coding for UMPSA STEMcube, a picosatellite simulation, where students will implement data collection and processing technique using Python. This will give students hands-on experience with real-world embedded system and IoT application. Microcredential course number 3 is Raspberry Pi Programming. In this course, we will explore how to program and interface with the Raspberry Pi Pico and Raspberry Pi 4 to develop real-world applications. Throughout the lessons, we will cover essential programming concepts, external hardware integration, sensor communication, and wireless networking. Whether you are a beginner or looking to enhance your skills, this course will provide hands-on experience in embedded programming and IoT applications. This course is structured into 5 key sub-chapters, each building upon previous one to give you a solid foundation in Raspberry Pi programming. So let's go over each and every sub-chapters briefly. In this chapter, we will introduce the Raspberry Pi Pico, its features, and how to set up programming environment. You will learn how to write your first Python script and run it on the Pico. Next, we will move on into control flow in Raspberry Pi. Here, we will dive into control flow concepts using digital input and outputs. You will learn about sequential executions, conditional statements, and loops by controlling LEDs and responding to button presses. This will help you to understand how programs make real-world decisions. Next, we will look into working with external libraries. Here, we will focus on using external Python libraries to work with additional hardware. We will install and utilize libraries to interface with OLED display, allowing us to display text and graphics using Python. By the end of this chapter, you will be able to integrate and use third-party modules effectively in your projects. Next, we will look into interfacing with sensors. Here, we will explore sensors communication using various protocols such as I2C, SPI, and UART. You will learn how to connect an accelerometer to your Raspberry Pi Pico, real-time motion data, and process sensor values in Python. This knowledge is essential for building interactive projects like motion control devices. And finally, we will look into long-range wireless communication using LoRaWAN and MQTT. You will learn how to send and receive data wirelessly using LoRa module, making it possible to create IoT applications for remote monitoring and control. We will also discuss power-efficient communication methods for real-world deployments.
Hi. I am Nurul Hazrina binti Nordin from UMPSP Lab, the Faculty of Electrical Electronics Engineering, University Malaysia Pahang Al Sultan Abdullah, the instructor for this course.
In this Chapter 1, Introduction to Raspberry Pi of our Microcredential course on Raspberry Pi Programming. This course involves integrating Python programming with hardware, specifically using Raspberry Pi systems, Raspberry Pi 4, and microcontrollers like Raspberry Pi Pico. By the end of this module, students will be able to develop functional Python programs that interact with hardware for innovative solutions. The learning outcomes targeted for this chapter is as follows. First, you will learn on how to set up Raspberry Pi operating system. We will guide you through downloading, installing, and configuring Raspberry Pi operating system on your device. You will learn on how to configure GPIO. Second is configuring GPIOs. You will learn how to enable and interact with the general purpose input-output pins for hardware control. Next, we will move on into installing Tony IDE. We will walk you through the installation and setup of Tony, a beginner-friendly Python IDE for Raspberry Pi. And you will write a simple Python script on an LED using Tony. So, the Raspberry Pi is a computer designed for IoT, automation, robotics, and learning. It runs on Raspberry Pi OS, a lightweight Linux-based operating system. One of its key features is GPIO, General Purpose Input-Output Pins, which allow it to interact with hardware components like LEDs, sensors, and motors. Python is the primary programming language used on Raspberry Pi, making it an excellent tool for learning programming and developing real-world applications. The Raspberry Pi 4 is a powerful single-board computer designed for a wide range of applications, from IoT to automation to AI and multimedia projects. At its core, it features a quad-core Cortex-A72 processor, providing desktop-level performance in a compact form factor. The Raspberry Pi 4 is equipped with multiple peripherals and interfaces, making it highly versatile. Let's explore its hardware. There are 4 USB ports, 2 USB 3.0 ports for high-speed data transfer, and 2 USB 2.0 ports for peripherals like keyboards and mice. Dual micro HDMI output supporting 4K resolutions on 2 displays simultaneously. Gigabit Ethernet port providing fast and stable network connectivity. Wi-Fi 2.4 GHz and 5 GHz. And Bluetooth 5.0 for seamless wireless communication. The 40-pin GPIO, General Purpose Input-Output Header, is one of the Raspberry Pi 4 most powerful features. It enables direct interactions with sensors, motors, LEDs, and other electronics components, making it an excellent choice for hardware projects and automation. This Raspberry Pi 4 supports expandable storage via microSD slot card, which is used to install and boot the operating system. For image processing and real-time monitoring, the boards includes a camera serial interface (CSI) for connecting official Raspberry Pi cameras, a display serial interface (DSI) for LCD touch screen attachments. The Raspberry Pi 4 requires a USB-C power supply with at least 3 ampere of current to run efficiently. Due to its enhanced processing power, it may require passive or active cooling, such as heatsink or a fan, for extended use under high workloads. Unlike the traditional microcontrollers, the Raspberry Pi 4 runs a full Linux-based operating system, enabling users to develop applications, run AI models, and even use it as a desktop replacement. With its powerful processor, rich connectivity options, and GPIO support, the Raspberry Pi 4 is an ideal platform for learning, development, and advanced computing applications. Whether you are building a home automation system, AI projects, or a robotics applications, the board provides everything you will need. Next, we will look into the Raspberry Pi Pico. So, the Raspberry Pi Pico is a compact low microcontroller board designed for embedded system, real-time applications, and low-cost project. Unlike the Raspberry Pi 4, which functions as a full-fledged computer, the Pico is optimized for hardware control and power efficiency. At its core, Raspberry Pi Pico features the RP2040 microcontroller, a dual-core ARM Cortex-M0 processor running up to 133 MHz. It is designed for precise control of electronic sensors, and it is low-latency, real-time processing. It has ultra-low power consumption, which is ideal for battery-powered projects. The Raspberry Pi Pico has 40 pins, including 26 multifunctions GPIO pins, enabling direct interactions with components like LEDs and motors, temperature, motion, and light sensors, communication modules like I2C, SPI, and UART. Unlike the Raspberry Pi 4, which runs on Linux, the Raspberry Pi Pico is programmed directly via MicroPython, or C or C++, making it simpler and more efficient for embedded applications. The Raspberry Pi Pico does not have onboard storage like the Raspberry Pi 4. Instead, it features a 2 MB of flash memory for storing firmware and programs, a USB 1.1 support, allowing users to program the board by dragging and dropping files like a USB drive. This simplicity reduces power consumptions and improve executions for speed for embedded system. One of the key advantages of the Raspberry Pi Pico is its low power consumption. It supports multiple power modes, including sleep and deep sleep modes for battery efficiency, 3.3 volt logic levels, making it compatible with many low power sensors. These features make the Pico ideal for portable devices, IoT applications, and real-time control system. While Raspberry Pi Pico lacks built-in networking and high processing power, it is a cost-effective, energy-efficient solution for projects like robotics, automation, and sensor-based applications. Now, choosing between a microcontroller and a microprocessor depends on your project's requirement. So, which one should you choose for your project? A microcontroller or a microprocessor? Choosing between a microcontroller and a microprocessor depends on your project's requirement. Let's have a look on their differences. A microcontroller, like the Raspberry Pi Pico, is designed to handle specific repetitive tasks with low power consumption. So, it is energy efficient, great for battery-powered applications. It can work real-time processing, whereby it can instantly respond to sensors input. No operating system is required. The firmware runs directly on the chip. However, Raspberry Pi Pico has limited processing power, so it is not suitable for complex computing, the one that involves a lot of calculations. It has no multitasking capabilities because it is designed for single-purpose applications. A microprocessor like the Raspberry Pi 4 offers high processing power, and it can run a full operating system like the Raspberry Pi operating system. It has a powerful computing capabilities where it can run applications, artificial intelligence applications, and multimedia processing. It is a multitasking device whereby it can handle multiple programs simultaneously, and it supports full operating system whereby this is ideal for development and research. However, take note that Raspberry Pi 4 requires higher power consumption. Now, this is not ideal for battery-powered devices. Microcontrollers like Raspberry Pi 4 requires an operating system where setup is more complex than the microcontrollers. So, which should you choose? If your project requires real-time control, low power consumption, and direct sensor interaction, go with a microcontroller like the Raspberry Pi Pico. If you need a full computing environment, multitasking, and operating system-based applications, choose a microprocessor like the Raspberry Pi 4. Understanding the strength and limitation of both platforms helps in making the right decision for your project. To get started, we need to install Raspberry Pi operating system. Follow these steps. Download the Raspberry Pi imager from the official Raspberry Pi website. Insert a micro SD card into your computer. Open the imager software, select Raspberry Pi OS, and write it on the SD card. Choose the SD card for the Raspberry Pi OS. Click on Write. Once completed, insert the SD card into your Raspberry Pi. Connect the power supply, keyboard, mouse, and monitor and power it on. Follow the on-screen setup instructions to configure your Wi-Fi, language, and system preference. Once setup is complete, your Raspberry Pi is ready to use. Open the terminal on Raspberry Pi, type the following command and press enter. Sudo Raspberry Pi config. Navigate to the interfacing options and enable SSH, I2C, and SPI. SSH allows remote access to the Raspberry Pi. I2C and SPI enable communication with sensors and other hardware components. After enabling these options, restart your Raspberry Pi to apply these changes. Now, we can use the GPIO library to interact with the hardware, such as controlling the LEDs and reading sensor data. For programming in Python, we will use Tony IDE, a beginner-friendly development environment. Let's explore these 3 ways to access and install Tony. The first method is installing Tony using command prompt or terminal in Raspberry Pi. Open the terminal in your Raspberry Pi. Type the following command and press enter. Sudo apt update and sudo apt install Tony. Once the installation is complete, you can open Tony from the Applications menu, Programming Tony IDE. This method ensures you have the latest version of Tony installed. The second method is the easiest because Tony comes pre-installed on most Raspberry Pi OS versions. Click the Raspberry Pi menu on the top left. Navigate to Programming, Tony Python IDE, and click Launch. With this method, you don't need to reinstall anything. Just open and start coding. And the third method is downloading Tony manually from the official website. This is useful if you are using Windows or working with Raspberry Pi Pico. Open the browser and go to tony.org. Click Download and choose the versions for Windows, macOS or Linux. Install Tony by following the setup instructions. Once installed, you can now use Tony on your PC to program Raspberry Pi Pico via USB. Now, your Raspberry Pi is fully configured and ready for Python programming. Let's move on to Activity 1, Digital Output LED On. Here's a step-by-step guide to program and wire a Raspberry Pi Pico to light up an LED on pin 14 using MicroPython. As we wrap up this chapter, let's review the key milestones that you should achieve in this chapter. First is to set up the Raspberry Pi OS. Second is to configure GPIOs and interface. Third, installing and configuring Tony IDE. And finally, the LED On project. In the upcoming chapter, we will look into control statements in Python and explore how to apply them on Raspberry Pi Pico to enhance your programming skills and create more dynamic projects.
Hello, hi. I am Nurul Hazlina binti Nordin from UMPSP Lab, the Faculty of Electrical Electronics Engineering, University Malaysia Pahang Al Sultan Abdullah, the instructor for this course.
Welcome to Chapter 2, Control Flow in Raspberry Pi of our Microcredential course on Raspberry Pi Programming. This course involves integrating Python programming with hardware, specifically using Raspberry Pi system, Raspberry Pi 4, and microcontrollers like the Raspberry Pi Pico. Students will design and implement real-world projects that combine Python programming with hardware components such as sensors, actuators, and communication module. By the end of this module, students will be able to develop functional Python programming that interact with hardware for innovative solutions. In this section, we will build on the foundational skills introduced in Chapter 1 by exploring control flow, one of the core concepts in programming. Throughout this lesson, we'll focus on these essential programming structures. Conditional statements that will allow decision-making, such as turning an LED on when a button is pressed. Loops, which automate repetitive tasks like a blinking LED. Digital input and output handling, enabling hardware interactions with buttons and LEDs. This module directly supports the overall learning outcome of this course, developing a functional Python programming using appropriate control structures. By the end of this chapter, you'll be able to write Python scripts that respond to user input, control external devices, and make logical decisions in real time. These skills are fundamental for digital making applications, such as implementing digital input-output using push buttons and LEDs. To control hardware, we use Raspberry Pi's GPIOs. Digital outputs control components like LEDs, while digital inputs allow the Pi to read button presses. Proper setup is necessary to ensure safe and efficient operations. In handling digital input and output and making decisions using Python, control flow determines how a program executes instructions. Understanding this concept is crucial when working with digital input and outputs, as it allows your Raspberry Pi to make real-time decisions based on sensors data or user interaction. In programming, control flow is managed through three types of control statements, which are sequential, conditional, and iterative statement. Let's go through each one with a flowchart example. The first type of control statement is the sequential statement. This is the simplest form of program execution, where instructions run line by line from top to bottom in a predefined order. For example, consider turning on an LED, waiting for a second, then turning it off. The program follows a structured sequence without any decision-making or repetition. Sequential execution is the foundation of all programs, ensuring that each line of code is executed in the correct order. The second type is conditional statements, such as if-else, which allow decision-making within a program. This is where the program checks a condition before executing specific instructions. For example, if a button is pressed, turn on an LED, otherwise keep it off. Conditional logic is widely used in real-world applications, such as security systems, smart home automations, and sensor-driven responses, where actions depend on certain conditions being met. Conditional statements like these if-else help us make decisions in our code. If a button is pressed, we can turn on an LED. This technique is useful for interactive projects like the smart home automation system and automation. Learning to handle this effectively enables more complex interactions between hardware and software. The third control statement is the iterative statements or loops. Loops helps execute tasks repeatedly without needing to write the same code multiple times. For example, we use a loop to make an LED blink continuously, turning it on, waiting for a second, turning it off, and repeating the process. Loops are essential for automation and real-time systems like the traffic light controllers, sensor-based monitoring, and robotics, where tasks need to run continuously. Understanding these control structures, sequential, conditional, and iterative statements, is fundamental for writing efficient Python programming on Raspberry Pi. Understanding these control structures, sequential, conditional, and iterative statement, is fundamental for writing efficient Python programs on Raspberry Pi. By applying these concepts, you can develop an interactive and automated systems, enabling your Raspberry Pi to respond intelligently to users' input and sensor data. Now that we have covered control flow, let's move on to hands-on implementation. Now that we have covered the control flow, let's move on to the hands-on implementation, where we'll apply these concepts to control GPIO pins with Python. This is an example of a sequential statements in Python. Import the GPIO library and configure pin modes. Set the LED pin as an output and write a program to turn it on and off. These steps is foundation for more advanced applications like home automation and robotics. Let's see how this works in Python. This is where you import GPIO library and configure pin modes. And then you write a code to turn an LED on and off. Time interval of 1 second is being stated by time.sleep for 1 second. Conditional statements like if-else help us make decisions in our code. If a button is pressed, we can turn on an LED. This technique is useful for interactive projects like the smart home system and automation system. Learning to handle inputs effectively enables more complex interactions between hardware and software. Loops help us execute tasks repeatedly. In this example, we will blink an LED in an infinite loop, making it turn on and off at 1-second intervals. Loops are essential for automation and real-time systems such as traffic light controllers and sensor-based alerts. Here's a step-by-step guide to program and write Raspberry Pi Pico to light up an LED on pin 14 using MicroPython. Here's a step-by-step guide to program and write a Raspberry Pi Pico to light up an LED on pin 14 when push button is pressed using MicroPython.
Hello, hi. I am Nurul from UMPSP Lab, the Faculty of Electrical Electronics Engineering, University Malaysia Pahang Al Sultan Abdullah, the instructor for this course.
Welcome to Chapter 3 of our Microcredential course entitled Working with External Libraries. This chapter is part of the course outcome of the Raspberry Pi Programming course, which involve integrating Python programming with hardware, specifically using Raspberry Pi systems, Raspberry Pi 4, and microcontrollers like the Raspberry Pi Pico. In this chapter, we will focus on working with external library, specifically using Python libraries to interface with an OLED. Throughout this module, we will cover installing the necessary libraries to enable communication with an OLED screen, displaying text and graphic on an OLED using Python, and interfacing with external hardware through Python libraries. In Python, external libraries are pre-written codes modules that helps us perform specific tasks without writing everything from scratch. When working with hardware, these libraries make it easier to communicate with devices such as sensors, display, and motors. For example, instead of manually programming how an OLED display receives data, we can use the SSD1306 library to simplify communications and control. This saves time and ensures compatibility with different hardware components. Before we can use OLED display with Raspberry Pi Pico, we need to install SSD1306 library, which is specifically designed for I2C based OLED screens. This library provides functions to write text, draw shapes, and clear the screen easily. Here's how to install it. Download the SSD1306.py file from the trusted source like GitHub, in which you can do so via UMP STEMLab GitHub. Open Tony IDE and connect to Raspberry Pi Pico. Copy the SSD1306.py file into the Raspberry Pi Pico file system. Import the library in your Python script using import SSD1306. Once installed, this library allows us to send commands to the OLED display using simple functions like text, show, and fill. Now that we have installed the SSD1306, let's write a simple Python program to display text on the OLED screen. Here's what each part of the code does. First, we insert the command to import the SSD1306. Then we initialize the I2C communication to connect the OLED with the Raspberry Pi Pico. The screen is cleared by using this fill 0 function. The text Hello OLED is displayed at coordinates 1010. Take note that this 1010 refers to the pixel coordinates X and Y. The show function updates the screen to make the text visible. This is the fundamental way to display information on the OLED. You can modify the text to show sensor values, notifications, or status messages for your project. This is an example of Python code. Follow the instructions sheet for activity 5A to display graphics on OLED. Beside text, the OLED display can also show graphics like shapes, lines, and images. This is useful for creating visuals indicators, dashboard, or even animations. In this example, we first clear the screen. The text graphics example is displayed at position 1010. A rectangle is drawn using rect 30, 20, 50, 30, and 1, where 30, 20 is the starting positions of the rectangle. 50, 30 is the width of the height. 1 means the shape is drawn in white on the black background. Finally, show updates the display to make the drawing visible. With these functions, we can create interactive visual display that react to real-time data, such as progress bars or graphics meters. Now that we understand how to display text and graphics on OLED screen, let's take a step further by integrating the external sensor, the BME280 environmental sensor, with our Raspberry Pi Pico. The BME280 is a compact, high-precision sensor that can measure temperature, atmospheric pressure, and humidity. It is widely used in weather monitoring, IoT applications, and smart home systems. In this example, we will read real-time data from the BME280 and display it on the OLED. This will help us to create a simple environmental monitoring system using Python. Let's have a look on how the code works. First, we initialize the I2C communication for both the OLED display and the BME280 sensor. The OLED screen will act as our user interface to visualize the sensor readings. Next, we create a loop that continuously reads sensor data, including temperature, pressure, and humidity. We then clear the OLED screen and update it with the latest readings, ensuring the display is always showing real-time data. Finally, we introduce a delay of 2 seconds before the next update, preventing excessive refresh rates while keeping the information current. This approach is fundamental in IoT applications, where devices must interact with external sensors and provide real-time feedback to users. Let's summarize what we have learned for this chapter. First, we look into external libraries. External libraries make it easier to interact with the hardware components. The SSD1306 library allows us to control OLED displays with Python. We learn to display text and graphics on the screen. Python libraries also help us connect with other external hardware like sensors. Mastering external libraries opens the door for more advanced projects, such as IoT devices that display real-time sensor data, smart home automation systems that provide visual feedback, graphical interfaces for embedded applications. With this knowledge, you can now integrate OLED display and sensors into your Raspberry Pi projects.
Hello, hi. I am Nurul Nordin from UMPSP STEM Lab, the Faculty of Electrical Electronics Engineering, University Malaysia Pahang Al Sultan Abdul, the instructor for this course.
Welcome to Chapter 4 of our Microcredential course on Raspberry Pi. In this chapter, we will explore how sensors communicate with microcontrollers using different communication protocols. By the end of this module, you will be able to interface an accelerometer with the Raspberry Pi Pico, read sensor data, and process it in Python. Communication protocols are the foundation of how microcontrollers interact with sensors and external devices. In embedded systems, 3 widely used protocols are SPI, I2C, and UART. Each of these has different speed, wiring complexity, and data transfer methods, making them suitable for specific applications. Understanding these protocols is key to working with various electronic components. Throughout this module, we'll connect an accelerometer to a Raspberry Pi and read the accelerometer data, working with I2C protocol for communication, and processing sensor data in Python. I2C, or Inter-Integrated Circuit, is a 2-wire communication protocol designed for simplicity and scalability. It consists of a serial data line, labeled as SDA, and a serial clock line, labeled as SCL. The master device sends commands, and multiple slave devices can respond based on their unique addresses. This protocol is widely used in sensors like temperature modules, accelerometer, and displays. SPI stands for Serial Peripheral Interface. SPI is a high-speed, full duplex communication protocol. Unlike I2C, the SPI uses 4 lines. The MOSI, which stands for Master Out Slave In, the MISO, which stands for Master In Slave Out, SCLK for Clock, and CS for Chip Select. This protocol is best suited for applications requiring fast and continuous data exchange, such as display and memory devices. And finally, the UART, the Universal Asynchronous Receiver Transmitter. UART enables serial communication between devices. UART is a widely used protocol that allows 2 devices to exchange data asynchronously, meaning without a shared clock signal. Instead, it relies on 2 main functions, TX or transmit and RX or receive. Let's begin with the TX function. The transmit pin sends data out from the device in a serial format, 1 bit at a time. Before transmissions, parallel data such as sensor readings or microcontroller outputs is converted into a stream of bits. The data is sent following a standard structure: a start bit, data bits, and optional parity bit. A start bit, data bits, an optional parity bit for error checking, and a stop bit. Now, let's have a look on the RX function. The receive pin listens for incoming data. When it detects a start bit, it begins capturing the data bits and reconstruct them into meaningful information. The received data is then converted back into parallel data for processing. One important rule in UART communication is that the TX of one device must always be connected with the RX of another. This ensures proper data transmission. Additionally, both devices must operate at the same baud rate, for example 9600 bit per second, to avoid data loss or corruption. UART is commonly used in microcontroller sensors, GPS module, and Bluetooth devices, making it a fundamental communication method in embedded system and physical computing. In summary, TX sends data, RX receive data, and proper wiring ensures successful communication. Each communication protocol has its advantages. I2C is great for multiple sensor connections with minimal wiring. SPI is ideal for fast data transfer but requires more connections. UART is a simple and effective for device-to-device communication, but is limited to one-to-one connections. Choosing the right protocol depends on your project's requirement. Accelerometer are sensors that measure motion, tilt, and vibration. They detect acceleration along three axes, X, Y, and Z. The X-axis represents side-to-side movement, the Y-axis represents forward and backward motion, and the Z-axis represents the vertical displacement. They are commonly used in robotics, gaming control, and fitness wearables. Many accelerometers, such as this MPU6050 or ADXL345, communicate using I2C, making them easy to interface with Raspberry Pi Pico. Additionally, accelerometers are often used in combination with gyroscope to measure angular motion, enabling the calculation of yaw, pitch, and roll. Yaw refers to rotation around the Z-axis, left or right turning motion. Pitch refers to rotation around Y-axis, tilting up or down. And roll refers to the rotation around X-axis, tilting sideways. This is an example on how to connect your accelerometer with Raspberry Pi Pico. Here is an example of Python script to read data from MPU6050. The Python script initializes I2C connections and send real-time acceleration data from MPU6050 sensor. The sensor provides X, Y, and Z axis readings, which can be used to detect motions and orientation changes. Let's move on to Activity 5 using accelerometer with UMPSA STEM Cube.
Hello, hi. I am Nurul Hajrina Nordin from UMPSA STEM lab with the Faculty of Electrical Electronics Engineering, University Malaysia Pahang Al Sultan Abdullah. The instructor for this course.
Welcome to Chapter 5 of our Microcredential course on Raspberry Pi. In this chapter, we will look into networking and communication, focusing on LoRaWAN for long-range communication, MQTT for IoT applications, and power-saving techniques in wireless data transfer. By the end of this chapter, you will understand how to integrate your Raspberry Pi Pico or Raspberry Pi 4 with LoRaWAN to send and receive sensor data efficiently. In many IoT applications, devices are deployed in remote locations where traditional Wi-Fi for cellular network may not be viable due to high power consumptions or costs. LoRaWAN is an ideal solution providing low power, long-range communication for IoT application. MQTT, on the other hand, is a lightweight messaging protocol used in IoT systems to transmit data efficiently. Understanding these technologies will allow us to build scalable and efficient IoT network. Throughout this module, we will look into the process of setting up long-range communication using LoRa and MQTT, the wireless data transmission and protocols, and understanding power-saving communication methods. LoRaWAN is a key enabler for IoT applications that require long-range, low-power data transmissions. With a LoRaWAN module connected to the Raspberry Pi, we can send sensor data over several kilometers using minimal power. This is especially useful in applications like smart agriculture, environmental monitoring, and remote assets tracking. We'll now walk through how to set up LoRaWAN communication in Raspberry Pi Pico. Take note that Raspberry Pi Pico can interface with LoRaWAN using SPI or UART. LoRaWAN operates using a star of stars topology. IoT sensors, also known as end devices, communicate with nearby LoRa gateway. This gateway then relay the data to network servers, which process the information and forward it to the application layer. This architecture ensures that low-power sensors can communicate over long distances without needing direct internet connectivity. The end devices or nodes are the IoT sensors or actuators that collect and transmit data. The LoRaWAN gateways act as intermediaries, receiving messages from multiple nodes and forwarding them to a central server that is known as network server. This server duplicates messages, manages devices connection, and ensures secure data routing where it is processed and visualized. The application servers is the final destination for the IoT data, where it is processed and visualized. This architecture enables IoT devices to communicate over long distances without requiring direct internet access, making it ideal for remote monitoring and smart city applications. Here's an example of sending a message using a LoRaWAN module with Raspberry Pi Pico. We initialize the LoRa module using the SPI interface and send a simple message. Hello, I am Nurul Hazrina. The data will be transmitted wirelessly over LoRaWAN to the nearest gateway. The setup can be expanded to send data in real time. Let's break down the Python code snippets that initialize the LoRaWAN communication module using the SPI Serial Peripheral Interface Protocol on a Raspberry Pi Pico. SPI1. This initializes the SPI peripherals. The Raspberry Pi Pico has SPI0 and SPI1 pin. The baud rate is 10 million. This sets the SPI communication speed to 10 MHz. The polarity 0 and the phase 0. These parameters define the SPI mode. Polarity 0 means the clock is low when idle. Phase 0 means the data is sampled of the rising edge of the clock. SPI is used to communicate with LoRaWAN receiver module such as SX1276 or RA02. Now, let's configure the LoRa module pins. CS assigned to pin 5 pin out configures GPIO pin 5 as an output for chip select. The CS pin is used to select LoRa modules when multiple SPI devices share the same SPI bus. Reset pin 14 pin out configures GPIO pin as an output for reset pin, RST pin. The reset pin ensures that the module is properly initialized before communication begins. LoRa assigned to LoRa SPI CS reset. This line creates an SPI instance of the LoRa class, passing the SPI interface and control pins. The LoRa communication now is ready to send and receive data. Once the LoRa module is initialized, you can send and receive messages using command like LoRa send. Let's have a look on MQTT, which stands for Message Queuing Telemetry Transport. MQTT is a lightweight messaging protocol designed for IoT applications. Unlike HTTP, which is complex and resource-intensive, MQTT is optimized for low-band, low-power communication. It follows a publish-subscribe model, where devices can act as publisher, subscribers, and MQTT broker. Publisher are devices that send data to a topic or an MQTT broker. Subscribers are the devices that receive messages from a topic. MQTT broker, a centralized server that manages messages distribution between publishers and subscribers. The model ensures efficient data transfer with minimal network overhead, making MQTT ideal for IoT applications such as home automation, smart agriculture, and industrial monitoring. The MQTT communication process works as follows. A sensor node collects data and publishes it to an MQTT node. The MQTT broker, such as Mosquito or HiveMQ, receive data messages. Any subscribed devices, such as dashboard or mobile app, receive data instantly. Since MQTT uses a lightweight binary protocol, it consumes very light bandwidth, making it perfect for IoT applications where network efficiency is critical. The Raspberry Pi Pico collects sensor data such as temperature or humidity. The LoRa module transmits this data as a LoRa packet over long distances. A nearby LoRa gateway receives the data and forwards it to the network server. The server processes the data and sends it to an application dashboard or cloud storage for further analysis. By using this setup, IoT devices can reliably send real-time data to cloud-based platforms without requiring high power or expensive cellular connectivity.